In this video, I want to take a look at rotations in R2 and R3. Now, what I have here is the table from the textbook, and I find it interesting that they seem to be able to just say, well, XY is going to W1, W2, and here's the formulas. It's like, where, how? Well, maybe within the text they did it, but it's not at all obvious to me where it comes from. However, I can get the matrix by looking at where does the standard basis go, right? So what I'm going to do here is I'm going to look at the point 1, 0 and the point 0, 1, and when I rotate the whole plane through an angle of theta radians, I want to know where does this point go, and that'll be my first column, and where does this point go, that'll be my second column. Well, the thing is with rotation, this length 1 here is still length 1 there. Just rotate it through that angle. And I want to know the coordinates of this point. So if I drop a perpendicular, then the x-coordinate of the point is the length of the side down here, and the y-coordinate is the length of the side up there. But I know trig. And I know that with a hypotenuse of 1, the adjacent side here is cosine theta, and the opposite side is the sine of that angle. So the coordinates of this point are cos theta, sine theta. And if you take a look at that first column, cos theta, sine theta is that coordinate. Likewise now, if I rotate this point, it's going to go over here into the second quadrant, still rotating through an angle of theta. And I want to find the x and y coordinates. Typically, I would drop the perpendicular down to the x-axis, but this one time, I'm going to drop it over here. The x-coordinate is this horizontal side, the y-coordinate is the vertical side. But see, I have this angle theta down there, and I also know that this was the point 0, 1, so the distance from the origin was 1. When you rotate it, it still keeps a distance of 1. So I've got a right triangle with a hypotenuse of 1. This is the adjacent side being cosine theta. This is the opposite side being sine theta. But in this case, because here in the second quadrant, this is actually negative. Right? If this is a small angle, the cosine is positive. Sorry, the sine is positive, and I want this to be negative though because I'm in the second quadrant. So the coordinates of this point are negative sine theta, cosine theta, and there it is right there, negative sine theta, cosine theta, my x and y coordinates of the spot where 0, 1 gets sent to. Now that I have this, it's not too hard to say, okay, multiply by xy and see that the x-coordinate, so the first coordinate of the output is going to be x times cosine theta minus y times sine theta, and likewise down here, x times sine theta plus y times cosine theta is that. So there's rotation in the xy plane. And depending on what you want to rotate through, you just change the angle. So for instance, some pretty specific ones. If you rotate through an angle of, let's say, pi over 2, so 90 degrees for those of you who don't speak radians. If you don't speak radians at this point, you really need to learn how to speak radians. So if I'm just plugging in a pi over 2 here, cosine of pi over 2 is, cosine of pi over 2, I quickly got a cosine curve in my head. Cosine of pi over 2 is 0. The sine of pi over 2, sine of pi over 2 is 1. This is a minus 1 and 0. So rotating through pi over 2, right, 1, 0 is going to go to 0, 1. But 0, 1 is going to go to minus 1, 0. So there's the minus 1, 0. Some other ones, rotating by pi, so half a turn. Cosine of pi is minus 1. Sine of pi, 0. Minus sine of pi, 0. Cosine of pi is minus 1. Notice, rotating by pi looks the same as dilating by a factor of minus 1, or reflecting and reflecting. Reflect across the x-axis, reflect across the y-axis. Sure enough, every point, x, y, when you rotate it 180 degrees, when you rotate it pi, it's going to end up exactly on the other side of the origin from where it started from. Okay. So that's that one right there. One last one while I'm looking at this. How about rotating by pi over 4? So let's put it over here. Theta equals pi over 4. Then the cosine of pi over 4 is 1 over the square root of 2. Sine is 1 over the square root of 2. Minus sine is 1 over the square root of 2. And 1 over the square root of 2. So there's the rotation by pi over 4. You may have had teachers in the past that always rationalize their denominators. I am not one of them. I think 1 over the square root of 2 is simpler than radical 2 over 2. Both numerator and denominator are smaller, and you still have a radical. So, anyway, this is the way I choose to write it. Now, let's take a look at rotations in R3. Now, rotations in R3 are interesting in that this is a big chart here. I'm going to have to move my window a bit. Now, we're going to look at 4 different rotations. One around each of the 3 axes, x, y, and z, and then around any random axis you care to choose. Now, you got to decide, are you rotating clockwise or counterclockwise? Of course, even as I do that, I'm in front of me, and if I say clockwise, it looks counterclockwise to you, and if I say counterclockwise, it looks clockwise to you. So I want to go counterclockwise looking at it, right? So if I'm looking straight down the x-axis and I rotate in a counterclockwise fashion, so that would be turning that way. What's happening is the y is rotating towards the z, and the z is rotating towards the negative y, right? And so this is very much like what it looked like with the x and y's. It's just that it's y's and z's now. Right? It's like rotation in the y-z plane, and nothing happens to the x-coordinate. So the thing is, 1, 0, 0 here goes to 1, 0, 0. 0, 1, 0 still will have an x-coordinate of 0, but then it's going to rotate like the last one we did right up above, right? So cosine theta, sine theta. And 0, 0, 1 is rotating this way into the negative y's over to there. And so it's 0, negative sine theta, theta. Right? So this little 2 by 2 down here looks exactly like what we did above, because it's just rotation in the y-z plane. Okay. Now, also, if I were to rotate around the z-axis, so if you look straight down the z-axis and rotate counterclockwise. Now each of these, as we say, clockwise and counterclockwise have a hugely determined by which side are you looking at it. Is my finger rotating clockwise or counterclockwise? I see it as rotating clockwise, but I'm pretty sure you see it as rotating counterclockwise because you're on the other side. So each time we do these, we're looking down the positive axis at the origin. So I look down the z-axis, or the x-axis on this first one. I'm looking down the z-axis towards the origin here, the positive z-axis towards the origin. So then I can decide what counterclockwise is. And so the x is being rotated towards the y is rotating towards the minus x, and there's that same rotation matrix that I had before in this upper left corner. Cos theta, sine theta, minus sine theta, cos theta. There's zeros down here because, you know, when you look at 1, 0, 0, where does it go? Well, it goes over here. It still has a 0 z coordinate. So there's a 0, just happened. There's still a 0 right here. And likewise, the y is being rotated towards the, 0, 1, 0 is being rotated toward the negative x-axis. It still has a z coordinate of 0, so that's that. And 0, 0, 1, of course, it's on the z-axis. As you rotate, right, as you rotate around the z-axis, that z-axis doesn't move. So 0, 1, 1, 0, 0, 1 still ends up at 0, 0, 1. And there's that last column. Okay. The one in the middle here is a little bit different because when I look down the positive y-axis and I rotate counterclockwise, the z is rotating towards the x and the x is rotating towards the negative z. So when I look at where does 1, 0, 0 go, it goes to something with a negative z component, right? And so it's cos theta minus sine theta. And likewise, the z goes into the positive x's, right? So 0, 1, 0. So 0, 0, 1 goes in over here. And so there's my sine theta, cos theta. This one seems backwards, right? Up here and down there, when you rotate around this axis, what's looking like horizontal is rotating up towards the vertical. Right here, we usually think of the x as being horizontal, rotating towards the vertical. But it's different when you look down the positive y-axis. The vertical is going this way and headed downhill. So anyway, the two positives are with the z, and the negative here is with the x, and it's going, well, it's the negative, it's the z component of where that thing in the x direction is starting from, right? 1, 0, 0 ends up with a negative z right there. So it's still the same sine, cosine, cosine, negative sine, but it's backwards because the minus sign, rather than being in the upper right, is down in the lower left. Okay. Just remember that. Now, rotation around any axis gets really complicated. And I'm not even going to try to derive it. Now, I can tell you how I would derive it. In fact, I use this quite often in a lot of the things, a lot of the things that I do. I create animations and such. And, you know, I have a juggler that juggles clubs. And so there's clubs that come up through the air and spin around, get caught in the other hand, and then they come spin the other way and get caught. And how do I get them to spin? Well, I multiply by a rotation matrix to change their orientation, and then I translate them to where they need to be. And then for the next frame, I rotate through a different angle and I place them where they need to be. And the club might be spinning around different axes depending on how the hand was holding, right? Your hands are holding the club like this, or they might be turned, and so you could be flipping them with different axes to rotate around. And so I would need to know what's the axis of rotation, right? What vector ABC is this rotating around? Right? Pick an axis and then rotate around that axis. And the way I usually calculate it is I say take this axis and rotate it so that it's in, let's say, the xz plane, and then rotate it up so that it's in the direction of the z-axis, and then do the rotation that I want, and then come back down and back over so that I start from. So to do this rotation around an arbitrary axis, I actually do 5 rotations. Move it over into one of the xy, into one of the planes, say the xz plane, then up to the z-axis, do the rotation I actually want, come back down and over. So that's 5 rotations. But each of those rotations is simple. The first rotation is a rotation around the z-axis. The second is a rotation around the y-axis. Then there's the rotation around the z-axis again that I actually want, down, over. Right? And so it's easier for me to calculate each of those 5 and then multiply the matrices together, and you end up with this. It's not pretty, but it is the matrix for rotation around any axis, ABC, in R3. So there you go, rotations.